Steve received his PhD in physics in Berkeley in 1976, and following some postdoctoral work at Berkeley, joined Bell Labs for almost a decade, where he did begin much of his pioneering research. He came to Stanford as professor of physics in 1987, and his research interest, if you look at his papers and publications, span many areas. They include atomic physics, quantum electrodynamics, polymer, and biophysics. Really a remarkable breadth of intellectual contribution and research. His pioneering research has been recognized by many awards and honors, as I'm sure many of you know, but notably the 1997 Nobel Prize in Physics for the development of methods to cool and trap atoms with laser light. So Steve was moved, let's say, he left Stanford and moved to Berkeley in 2004, where he became director of the Lawrence Berkeley National Laboratory and professor of physics. And Steve's bold and visionary leadership has really set the stage to take Berkeley Lab into new directions, tackling remarkably complex problems in areas that include global warming, carbon emissions, and new and sustainable forms of energy. Steve joined the Obama administration in 2009 as the Secretary of Energy. And let me end by just a personal comment. I knew Steve when he was here on the faculty, and I recall extremely well his passion for science and discovery, and in particular, a very keen interest in interdisciplinary research. He was one of the few faculty who recognized opportunities to come together across disciplines and worked tirelessly to begin what came to be known as Stanford's BioX program, of which I think some of you are probably familiar. It's innovative and now extremely successful. At that time, it was a new thing, but it brought together the physical and the biological sciences and the engineering and medicine into one umbrella, really, a physical home, but much broader than that, that has really made a transformational, I think, effect on how research is done in this broadly defined area at Stanford. So please join me in welcoming Steve to deliver the keynote and closing address for the symposium.
Thank you, Keith. Okay, I'm going to try to figure out. I guess I'm going to have to look at what I don't need that microphone. No, then I'm going to be. I have a look. That's great. Fantastic. Okay. Then I'm liberated. Okay. Great to be here, and I'm sorry we're running late. I'm staying between you and dinner. I know that's tough, but let me tell you, it's a lot easier than going to oversight committees. But anyway, what I want to tell you about is I'm going to start by reinforcing, I don't have to tell you, but just remind you how important technology is in not only advancing science, but advancing many of the things that help shape the world. And tomorrow we're going to reminisce about SLAC. But the history of SLAC, I think, goes back a little further than what I think Bert will talk about. It goes back to the time of Terman and the time of when there was this Silicon Valley starting, and in particular, the Russell brothers, the Varian brothers, Russell and Sikora Varian, inventing the klystron, and then people like Bill Hansen, Webster, Williams, taking advantage of that invention and making accelerators. And so this is one example of how an invention can really transform a field of science, not science but engineering, has to do with radar and everything else. So I'm going to talk now about other inventions and developments that transformed the world in many ways. There's a recent article that just came out this week's issue of Nature, written by Arun Majumdar and I, a real labor of love. Arun's here, and he and I spent many sleepless nights, bunches of weekends and nights consecutively writing this. I know he was doing a lot of family events. He was no longer, when the tail end of this, he was no longer working at the Department of Energy. I just have to say that my wife also suffered on this because you do this at nights and weekends. And one time I came home, it was a Wednesday, early evening, 7 or 8 o'clock, there's a little note. Dear Honey Bun, I've gone to the Maryland shore. Tell me when the papers are finished. So anyway, so it's going to have a little slivers of what's going on there. But the article starts with just a very quick 1-paragraph, 2-paragraph review of the Industrial Revolution. And the Industrial Revolution, in allowing for power well beyond the access of humans and animal power, really transformed the world. And this is one of my favorite paintings where it reminds us of the setting of a glorious wind-powered boat. Lots of symbolism here, the ugly belching coal-burning steamship towing this warship, historic warship, to get dismantled for scrap. But it was a setting of the sun for one era and a rising of another. And this, plus all the other things that really transformed the world. Another invention came a bit later, was the internal combustion engine and liquid fuels. And if you look at this New York scene 1890, and you look at what Detroit looked at 1920, this was one of the most remarkable transitions which you needed an extensive infrastructure, and how rapidly you went from horse-drawn carriages and horsepower to horsepower. But this transition was also aided, ironically, by an environmental concern. What was the environmental concern? The environmental concern was that in, for example, New York and Brooklyn, there were 160,000 horses, and by 1880, they were producing 3 to 4 million pounds of horse manure a day. So it was piling up. The fertilizer market was completely saturated, and it was piling up in lots, story high. There were entrepreneurs that would sweep the streets for well-heeled people so they can walk across the street and not have to walk in manure. Okay? So that was the condition at that time, 1880. And so this even though there was a lot of opposition, the incumbents were the horse guys and agriculture, and they were very much against these moving bombs, these automobiles with this explosive stuff. And they tried very hard, and there's certainly lots of congressional testimony about how dangerous it was. Anyway, and it also scared the horses. Here's another environmental concern. This is a temperature record from 1800 to 2010. And it shows over this period of time that the temperature of the Earth averaged is rising. It doesn't look like much of a rise. It's, from here to here, this is 1 degree centigrade. Doesn't look like much at all. I mean, it changes by tens of degrees centigrade in one day in Chicago. But let me remind you what we're talking about. When you change by 5 or 6 degrees centigrade, you go from where we are today to the ice ages, the last ice age, where Canada, then the United States down to Ohio, Pennsylvania was covered year-round in ice. So that's 6 centigrade change. Okay, so we're going up so far by about 1.8 from this time here. And the question is, what are we going to do? A lot of discussion was made that climate isn't changing because it hasn't changed significantly in that period of time. But nevertheless, if you look at a longer record, it seems that something is happening. Okay, what it might be due to. This is the CO2 concentration. This is the population of people. That was 1770, the nominal beginning of burning coal and steam engines. Also, around that time, from 1750, you see other greenhouse gases going. Now, the question is this just a coincidence that carbon dioxide is on the rise at the beginning of the Industrial Revolution? And we do know this is a physics thing. It is a greenhouse gas, and there are other greenhouse gases that trap the heat. All right, but it may be that the carbon dioxide just happened to be increasing about that time, but what's the proof? It's due to humans, okay? So let me give you a little snippet of some of the proof that is remarkably not talked about that much. And it has to do with carbon-14. There's also carbon-12. I won't tell you about that story. Carbon-14 is made in the upper atmosphere. Bombardment of cosmic rays, protons hit nitrogen-14, make carbon-14. It's radioactive, it mixes, it diffuses down, it gets incorporated to all living things. You and I have lots of carbon-14 in our bodies. Now, suppose you die. Now, if you just kind of die and you don't take good care of your remains, you get recycled well within the lifetime of carbon-14. Trees grow, they die, they get recycled, 100-year, 200-year lifetime, 5,000-year lifetime of carbon-14. However, suppose we take you and put you away, sealed up, away from the environment and the biosphere for 10 million years. Too many lifetimes. You are no longer have any carbon-14 in you. Now, you take all those remains and you put them back into the atmosphere, and it's significant. You are now introducing carbon, which is not in equilibrium with the cosmic rays and what's happening in the biosphere. You know, if you just had a steady state, that wouldn't be doing anything. So if you put in a significant amount of non-radioactive carbon, you might change the isotopic abundance of carbon-14 with normal carbon-12, and that is that isotopic abundance. So as the carbon dioxide increases, this goes down. Now, something strange happens around 1950, so let's go into that. Carbon-14 starts to zoom up about then. This is actually due to atmospheric testing of H-bombs. So that's introducing another thing. And so now you have in the northern hemisphere this spike of carbon-14 ratio to carbon-12. There's about a year delay because the testing is in the northern hemisphere, mixes with the southern hemisphere. That movie and book On the Beach was correct. The southern hemisphere, if there's a big radioactive cloud, it hits Australia and New Zealand last. And so that's that delay. This starts to go down. It starts to mix with the ocean, first the northern hemisphere ocean, then the southern hemisphere ocean. So this isotopic trace is actually telling you in great detail atmospheric mixing, upper atmosphere with mid and lower atmosphere, the absorption of carbon into the ocean, the equilibrium. And then it's going down here. And so what about this? Is that rate consistent, or is, what's going on? Now there's another much slower mixing of surface ocean with deeper ocean. But if you look at this rate down here, it turns out it's going down too fast. And it's completely quantitatively beginning to be, with smaller and smaller error bars, consistent with, we know how much carbon-12 we're putting up from burning fossil fuel, and that dilution effect is consistent with this slope. So that's more of a fingerprint of humans. If it's just a natural thing, some changing thing, you would have to be releasing, it doesn't prove it because it could be deep recesses of carbon fossilized or methane hydrate buried for a long time, but it's again a suggestion that it's more than just a coincidence. All right? So there's more of this stuff going on. This is the Keeling, son of the Keeling who first showed the detailed rise of carbon dioxide in the atmosphere. Okay, so the climate's changing, and are we seeing some effects? Well, certainly we're seeing a number of effects, especially if you go to the northern part, but let's say in the United States, here's some other, we'll call them effects, that may or may not have to do with climate. For example, we don't think earthquakes have much to do with carbon dioxide in the atmosphere, and so over the last 30 years, they've been hobbling around like this. This is very noisy data, as you see, but if you look at all the extreme events like floods and storms, you look at the wildfires, the droughts, and things like that, there seems to be a perceptible rise going on. Now, again, it might be just a coincidence that the climate models predict some of this stuff, and climate models cannot predict very accurately at all, really, tornadoes, or thunderstorms, or even hurricanes. But they do a reasonable job at predicting changes in temperature extremes. They only did a moderate job of predicting floods. They underestimated. But other than that, so there's lots of uncertainty here. But that's what we're seeing. And this is the insured. This is This is from Munich Re, a reinsurance company, this slide and the previous slide. And this is the trend line of insured and uninsured losses. The first one had nothing to do with monetary value. It just had to do with number of events. So it's more natural physical stuff. And this is just to put a monetary value on it. It's increasing. So whatever's happening, there may be some monetary value associated with this as well. There's also a little bit other stuff associated with, you may not remember, but I'll remind you, in 2003, Europe had a big heat wave. Over 50,000 people died in that heat wave, 2003. Moscow had a heat wave in 2010, 10,000 to 15,000 deaths. And Chicago had a heat wave where it was actually much smaller. The official count is 739, but there were 250 bodies found in the following week that weren't autopsied. So there might have been more. Okay, so these heat waves do have real cost. All right, so addressing the energy and climate challenge is really, it's a challenge, but it's also an opportunity to promote sustainable growth. And the question is, well, the economics force the issue. And by that I mean, for example, there are a number of people predicting peak oil. Then we'll go off of that because we'll run out, and then we'll have to figure out something better. Okay. So let me tell you what's been happening from 1966 to 2011. This is the amount of oil. Hey, it is going down. This is the fraction of oil used in fraction of energy in the world. Oil's going down, coal's beginning to go up. Natural gas is steadily climbing. I'll talk a little bit more about this. These are renewable. That green is renewables, nuclear, and hydro. So we're using, and if you look at the absolute numbers, we're using a lot more oil. The question is, are we beginning to run out? Are there good signs that we're running out? The answer is not really, because the technology is rapidly improving in both finding the oil, being able to extract more and more, a higher and higher fraction of the reservoir. Nowadays, routine extraction is, they're aiming at 50%. 2 or 3 decades ago, they were happy to get 30% of the oil out. In some places, they're getting 70%, 70. Okay? So these are the reserves, worldwide reserves, and the ratio of reserves to production is remaining roughly constant, but it doesn't include the shale and gas reserves. Okay, so that's really changing the world. In the United States, we've increased the oil-like production, this is gas, liquids, and shale oil, by 500,000 barrels a day increase in production in the US. It's going to go up another 1 million a day. We're the number 3 producer of oil in the world. We will be number 2, just a little bit behind Saudi Arabia within 5 or 10 years. Okay? And so we don't know how much longer this will last, but a couple of decades and more. Okay? So we're not going to be running out in 30, 40 years. Renewable energy, a very good news story. Went up 5.5 actually from this to this. And this is the extent. It's not only in North America, but it's really in many parts of the world. That's the good news. The bad news is the carbon-free sources of energy have actually remained roughly constant, or it's actually going down, because as the renewables went up, hydro and nuclear went down. And nuclear is continuing to go down because of, well, Japan's still working through this, but Germany has worked through this, and Japan probably won't be at maybe half of, or at best half of what they originally planned. And hydro's going down because there's a lot more increasing pressure to breach dams, just so you know, okay? So there we have this. Now, if you look at the International Energy Agency, IEA, they're projecting the levelized cost of electricity. This is all the cost of electricity. It takes into account over the lifetime of the asset, the construction, the operation, the maintenance, the fuel cost, the cost of capital. I think they were using about 8 or 10% interest rates, all that stuff. And this is what, so the blue is when there's no price on carbon. This is what it is. But actually, in reality, in the US, the cost of natural gas is here, right now. So in many other countries, it is considerably higher, but in the US, it's right now here. I should also say, and I'll return to this, we don't really know what the real cost of carbon capture is because we don't have commercial scale stuff going on in the world yet. So that's not known. This is an estimate of what you'll achieve in 2020, and I will talk a little bit more about it. This is not accurate, neither is this. This is probably okay. Okay, so now let me talk about the opportunity. I want to remind you of what Andy Grove said in a book, Only the Paranoid Survive, and how to exploit the crisis points that challenge every company. So I'm reminded of this old Hungarian saying. It's Hungarian for G, which means crisis, but it's actually a two-character word, and it's a combination of danger and opportunity. Okay? So they got it right. Those Hungarians were smart. Okay, so what are the opportunities? Well, I'm going to talk about just little parts of two things, energy efficiency and clean energy sources. So let me talk about energy efficiency. First of all, things have gotten very energy efficient. If you look at today's modern airplanes, they only use 30% of the fuel of a 707 with better performance. It's remarkable. It's due to amazing improvements in aerodynamics, the engines, and very lightweight materials like carbon composites. The engines they're not plateauing. They're getting better. The next generation of engines, not only Pratt & Whitney, but GE, are going to be this much better and this much more efficient. For the same amount of fuel, you get that much more thrust, or you use that much less fuel. This is significantly less carbon, and it's 50% quieter. All things are going in the right direction. With this, Department of Energy is working with both Pratt & Whitney and GE, helping them do very high-performance computer calculations of how to improve these engines. It's a very, very sophisticated fluid dynamics calculations. What about materials? So let me tell you a little story about materials. If you go to Washington, D.C., the Washington Monument, and you look at it, but you probably may not know that the Washington Monument is capped in aluminum. Okay, so why would we cap the Washington Monument in aluminum? The father of our country, for God's sakes. Why would it be so cheap? So in 1884, when it was completed, the price of aluminum was $1 an ounce. And the price of gold was $20 an ounce. So what happened? Aluminum 6 cents an ounce, and gold has a very patriotic price, plus or minus $200. Okay? What happened? Well, a lot of things happened. But what happened primarily is there was a fundamentally new way of processing aluminum. It's electrolytic reduction of the aluminum. Okay? And we are working on whether you can make titanium. Right now, for aircraft-grade titanium, you have to remelt refining steps at 1,660 degrees centigrade. That's very, very hot. And you can do electrolytic reduction the way you make aluminum these days, perhaps at this temperature, 9 times less energy, 5 times less cost, if it works. Titanium is not quite as abundant as aluminum or steel, but it's up there. It's only the processing costs that make it really expensive. And so, so that would be good. Now, there can be even better things. If you look at carbon composites, right now, if you look at what, these are very strong, lightweight things that make up the wings and part of the fuselage of the modern-day airplanes. The carbon fiber itself is an imitation of what we learn of thousands of years of natural fibers, like cotton and silk and wool. You take the little fibers, you string them together, and you make them into a long fiber. Then you've got really long fibers in these spools, and then you put in, you mix it with epoxy-like materials, and you make this stuff. Okay, very intensive process. So now, let me talk about really inexpensive plastic, injection molded thermoplastics. When I was a little kid, I made model airplanes. These exquisitely precision parts that squirt in, they go up, and they're made this way, but they're not strong. Thermoplastics are not strong like carbon fiber. You can't do this because you've got these long fibers. So just throw this out. This was a one-liner in this Nature article. What happens if you use carbon fibers, either nanotube or microtube, but micron by 300 or 400 microns, or half a micron by 300 or 400 microns, all squirtable, but then do something to the ends. So you trigger the chemistry that they can co-link. You might get 80% of the strength, maybe not, but it's injection moldable. Okay, so that would transform this very lightweight material, and then you can make very complicated parts that would erase the price differential. But right now, it's too expensive. Even lowly steels haven't improved. The mild steels that we used to make our cars out of, and mostly still do, have a tensile strength. This is, you take the steel, you squish it, and how hard do you have to push before it starts to give and change in elongation. And so that's why it's pressure versus fractional elongation. This is the kind of crappy steel we make our cars with today, mostly. But because of the higher gas mileage, the European and Asian cars have much more of the good stuff. Look at this. This is 200, 250. You're actually making steels out here 4 times, not 40%, 4 times as strong tensile strength. And so these are very, very strong structural members that keep your car safe but much lighter. Okay, now the question about is, do we understand these steels? And the answer is not really. We know if we take it and we put in some special mixtures, then you pound it, and you shake it, you bake it, you pound it. You know what, this is how you make samurai swords, this is how you make a lot of stuff. And we actually know that when you do all those things, you create properties. Now we have wonderful analytic tools to know if you do things in this order, this temperature, whatever, there's nano, meso, and micro and macro structures that are very, very sophisticated. Now the question is, can we actually predict how to make, we got the properties over here, we now have the characteristics, but we can't predict what we do. We just do it and then measure it. And so if we can get to a point with computation where we can actually predict what will happen, you can start to explore parameter space in a very deep way. With very high performance computing, it may be possible. So this is another exciting thing, not only in steels, but in a lot of these alloy materials. Still on energy efficiency, if you look at a combustion engine car, this is actually a composite car of 70% gasoline and 30% diesel. So you look at a passenger vehicle car. So you look at the fuel energy. This is the thermodynamic loss. It's a lot. And at the mechanical power, this is the friction loss. This is the air drag loss. And the friction losses end up, this is the stuff that actually is used to move the car. And you're accelerating this, 4,000-pound thing. So it turns out that first you can improve this a lot. Next, you can improve that a lot. And I learned yesterday that even brakes, there's brake recovery, but the brakes today, like the disc brakes today in the car, I learned it maybe day before yesterday, they're 1% of loss because when you're not putting your foot on the brake, they don't fully release. Bet you didn't know that. I didn't know that until day before yesterday. And we can fix that. Okay, but there's a lot of other things that haven't been part of the thing. The most vehicles, virtually all the glass in cars, you have these very good sputter coatings that you use in building windows, low emissivity things. They block the ultraviolet, they block the infrared. They keep the visibility 60, 70%, at least 50%. You can't tell the difference. But they block a lot of the heat gain. They block the heat loss. Okay? Your car, if your car had that glass instead of the other things, you wouldn't need those, things that you put up in it. So it stays, but nope, they're not in there. But it'll cost a few bucks more. Okay, lots of stuff that has not been incorporated into the efficiency of cars yet. So there's a lot of things we can do. Aerodynamics. You know that you got really great aerodynamics in trucks. When they discovered this, within a year or 3, virtually every truck on the interstate started having some either very modest or more streamlined versions of this. Here's another thing. So, we do these simulations in the supercomputers we have at the Department of Energy, and then it was discovered that if you put a little wedge of plastic down here, you could actually save 5 to 10% fuel just from that part. And then they said, well, it costs a little too much, so they value engineered it. And then they found that they can make the piece with only slight design. You get a little bit worse. You're still in the 6% range. Well, here's the cat's meow stuff, but you're down in this range. With a $1,000 piece of plastic, one person could snap on the bottom of their truck. So we're hoping that this will take off. Again, it seems modest, but these trucks use a lot of gasoline. These long-haul diesel trucks average 100,000 miles a year, $80,000 in diesel fuel. It's a big deal. 20% of the transportation energy is in long-haul trucks. Okay, we have internal combustions that are improving. This is one diesel Jetta, 43 mile per gallon highway. The engines are getting better. This is a new 1 liter Ford engine. It has a footprint of 8.5 by 11 sheet of paper. So it fits on an 8.5, 11 sheet of paper and is about that tall. And this little baby gives 118 horsepower, 125 pounds of torque. Okay? I used to have a 2 liter engine car that gave 96 horsepower. And so these are improving. If you allowed the octane of US gasoline regular to go up to regular Europe octane, you can increase the thermodynamic efficiency of internal combustion gasoline engines from about 30% to 40 to 45%. You can start to achieve diesel-like efficiencies with the new technology, direct fuel injection, layered, all this other stuff. And actually, if you blend in alcohols like 15%, the octane automatically goes up a little. And so, there are elements in our industry that don't want that to happen, and it's not the automobile industry. We are helping design better internal combustion engines. This is an engine, a diesel engine, low pollution engine designed in silico. High performance computing, this is the injection profile, but with a lot of back and forth with lab diagnostics. So this is laser diagnostics of an internal combustion diesel ignition. So you go back and forth about what's really happening. Very, very complex fluid dynamics and chemistry going on, all non-equilibrium stuff. So it was the optimized parameter space on a supercomputer with verification in this laboratory setup. And then they built a prototype, and it worked according to what it said. And they said, and then we went into production. They went into production, Cummins. Okay? So again, this is very useful, good, beautiful science, engineering that's going on. Electric vehicles, although all electric vehicles or plug-in hybrids is another opportunity. This is a Chevy Volt, just in case you didn't know. And this is the $109,000 Tesla, and this is the new Model S that's coming out in various grades and ranges. Lots of things happening there. The Fisker has an energy density using this iron lithium phosphate of about 100 watt-hours per kilogram. The Tesla and the Chevy Volts are using 200 watt-hours per kilogram, so that's now state-of-the-art being commercialized. There are other battery manufacturers working on these things. This one is planning to undergo extensive safety testing. And then there are a number of other companies. I just included one, but there's a whole bunch of other companies shooting for this goal. Okay. So the improvement in batteries has been slow and steady and continued. But really over the last 5 and 10 years, it has begun to accelerate. Dramatic, great ideas in battery technologies. Very, very novel technologies. We're hoping, once you get into this range over here, with the same processing costs. You just drop the price from this range, 4x, and except for one part, and that we're addressing that as well. And that is, it's not just the battery cell, because right now the battery cell is 3/4 of the cost of the battery, but you're only using about 60, 50, 70% of this cell capacity for detailed reasons, a lot having to do with safety. And so if you can actually get a battery system with appropriate diagnostics and electronics, you can actually use more of the battery. You can run it closer to what it was meant to do. And let me just give you an example. The last 5% charge on a lithium-ion battery, when you go from 95 to 100% charge, that's where a lot of the damage is done. Remarkably, your computer, your laptop, doesn't give you a chance to limit that amount of charge to hold it at 95%. Maybe not so remarkably, because you got to buy one if you're a heavy user every year and a half. But you can monitor that. And you can, because it's that last little bit when you have a loop, but you're trying to push it in harder and harder, you could have a temperature runaway, which can cause dendritic growth, can cause all sorts of stuff. You want to limit that. You would want to measure what these things are doing in terms of temperature and everything else, so you can know when to back off and when not to back off. Okay? So a lot of what we're trying to do in the Department of Energy now is we're starting new programs to show that it's the systems approach to a battery and the electronics and the control, including the control of the electrical thing to the motor, is a very big deal that's been not really paid attention to sufficiently, but it's something low-hanging fruit, so to speak. So let me go to clean energy sources. I showed you the IEA, the International Energy Agency, predictions of energy costs by 2020. To be fair, I'll show you the EIA. This is the U.S. Energy Information Administration. This is part of the semi-autonomous independent part of the Department of Energy. And this is the cost of various forms of energy, electricity generation, conventional coal, natural gas, this and that. These are the uncertainties. This prediction was made in 2010, and these error bars are the uncertainty of what they might cost in 2016. Okay? So what are those little green symbols? They're 2012 actual prices. So they were outside of the uncertainty after only 6 years. So why? Well, so Arun and I spent a bit of time trying to figure out why. But I'll tell you in 2 sentences. If you don't know what's happening today in the lab and today in the prototype, and you only look backward in time, you're going to be a little bit out of date. And when the technology begins to improve rapidly, you're going to be more out of date. And so you want a technologist to begin to get a sense of what's going on to make a projection of what might happen. And it turns out if you get a technologist that has that sense and has a little bit better economics training, you can make a better prediction. So like I said, this is $100 a megawatt hour, 10 cents a kilowatt hour. That was the IEA prediction, but we're down here. There's other sources, and we spent a long time. So this is Bloomberg New Energy Finance, and trying to make a kind of a sociological economic prediction. What they tried to do is try to actually look at real prices and contracts, and then back out the subsidies and all that other stuff. And so the cheapest is natural gas. It's down here. This is natural gas assuming $4 a million BTU. Right now it's $250, $280. But that's not sustainable because you're not extracting it, $250, $280. But so at $4, there's a very, very historically low prices. Natural gas is still going to come in as a winner. But look, large hydro is here. Wind onshore is here, but it's a tail here. Silicon, crystal silicon, silicon tracking PV, they're here. Okay? This is a little different, especially with stuff you can put on a rooftop because it's a semi-competition between retail and wholesale, but these are wholesale prices. So this is actually very good news. And if you look at what they published a year before this, their third quarter 2012, these were all back 15, 20%. So the learning curves on a lot of these technologies is advancing very rapidly. And so that's all good stuff. Let me talk about wind, which was underestimated. You look at this is at 80-meter tower. That's a pretty tall tower. And you look at these wind speeds in meters per second, and you see these purple and all this other stuff, and you go down to even the orange, the brown, even the gray. You get a huge swath of the United States having pretty good wind sources. And just remember these numbers, like 7 meters, 6.5 meters per second. That's down in here. That's all this gray stuff. Okay? That's 5.5 meters a second. So that's wind speed at 80-meter tower. Now, as you go higher and higher, there's a kind of a drag on the wind as you go on the land. And so this is 2002 standard technology, 2009 standard technology. You're getting better utilization. As you go higher and higher, you go to 80-meter towers, you're especially gaining at the poorer wind sites, but you gain a lot. You gain a lot, so there's a lot of things happening. The aerodynamics are getting better. You're actually taking a systems approach to the wind farm, so you're not looking at an isolated wind because there's wakes, the other things. Remember, this is levelized cost of electricity, so if the maintenance costs go down, that improves everything. If the lifetime goes up, that improves everything. All these things are taken into account. Size is a big factor. This is a 100-meter wind tower, 100-meter wind tower. This is offshore 115-meter tower. The diameter of this blade, this is a boat, it's really a ship. Let me give you a scale for what 100 meters are. The largest wind turbines installed is 5 megawatts. It's 126 meters. There's 146 meters, 7.5 megawatt on the drawing boards. That's offshore. This is going to be the limitation of onshore because the single length of the blade is so long, it won't make the turns on a railroad track or on a highway. So you're going to be naturally limited to the size on land, but you can go up and up and up, except for one thing. And you can see it right here. You're installing this in very calm seas. Now suppose there's 3-foot seas. I learned firsthand on Macondo for a couple of months, a lot of things stop at even 3-foot seas, and in 60 seas you can't do anything. And now 100 meters tall, or 120 meters tall crane, you ain't going to do much. Just to give you a scale of it, the Airbus 380, the biggest plane up there, is an 80-meter wingspan. So look at these numbers. And Wright brothers flew 37 meters in their first flight. So these are big. Here's a one-liner in this Nature article we wrote. It said, one approach to service the highest wind turbines is design cranes that can inchworm themselves up the towers, analogous to self-lifting cranes used in tall buildings. This paper is a concoction of one-liners. So now I get to explain what I mean by this. Serviceability, especially offshore. You can't do this. So if you're offshore and you're in North Sea or someplace like that, you may be down for 3 months, and that means loss of income for 3 months. That would be disastrous. So you need serviceability. This is an inchworm. That's how it crawls up. So you can have this thing, you know, go up the tower and hold on to the tower, and on top of it's a crane. That's how we build skyscrapers. So the tower itself is a structure. You put that on the ship, low down, and you go, you know, your 3-foot prong thing, it goes. This is, they got 3 of those, and they got 3 of those, and you kind of look at the inchworm, you say, this makes sense. So maybe it will work. Okay. Power conversion. Here's another thing which is something we are looking at very hard. The size of transformers scale roughly, it's a very complicated thing, but it scales roughly in the inverse of the frequency. So if you go at 60 hertz, you have to be big mother things. But if you go at 60 kilohertz, okay, it's 1,000 times, in principle, 1,000 times smaller. Well, it's not going to be 1,000, but it's going to be, it could be from room size to a suitcase size, okay? So we're looking at power electronics. We're also looking at power storage, driven now by potential automobile market. And when this thing happens, which is the storage of pumped hydro, you can get ubiquitous storage everywhere in the world. And so this is a target for us in the Department of Energy. And right now, 30% of electrical power flows through power electronics, but by 2030, 80%. And yet, most universities don't have faculty who teach power electronics or research programs. And the world is dying for this, okay? And there's really cool, sophisticated stuff that you can do in power electronics, and it's really important. So you will get a job, guaranteed, if you're a competent power electronics master's, PhD, also would help. Solar, let me talk about, so these are called learning curves. Logarithmic graph, $110 per watt. This is the cumulative production. So when you go tenfold in production, you go down a certain fraction, you get another tenfold in production, a certain fraction. That means the price equals a quantity shipped to some power. Okay, it's power law. Remarkably, technologies follow these learning curves. Moore's law is a kind of a variation on it. It's linear in time, but it turns out that it can be. So anyway, this is the learning curve for crystalline silicon prices. And this was, I think this was made in 2010, this graph. And 2015, they predicted this was large subsidies, a little shortage, a correction in shortage. And they were predicting it would get to $1 watt by 2020. Sorry, this was a prediction, $1 watt 2015, that's not right. Oh, this is the module price. That is right. Okay. Just module price. It's not the full price. Okay. So what happened is this is the module price 2012. This is logarithmic, right? And so it's 86 cents today. Okay. So we spent a long time thinking about what the Department of Energy could do. The full price in 2004 was about $8, full installed cost, levelized dollars per watt, levelized cost. By 2010, the price went down to a little bit less than $4. This is the module cost. This is everything else. Everything else means the power electronics, the land use, the balance of systems, all sorts of stuff. And so we decided, okay, the module price, the module price is $1.70. You know, by 2020, could we get it down to 50 cents? You know? And so for the first year or two, some of the people in the industry thought we were smoking something. But last year, they said, you know what? You made us go back, and you helped us go back and replan our business plan, and now we decided that's very achievable. Okay? That's happening now, and oops. And let me just say that now it's 86 cents. Guess what? The cost of solar is actually dominated by all the other stuff, not the module. And that will be true of batteries within 5 years. The cost of batteries will be dominated by all the other stuff, not the cell. 10 years at the outset, but probably 5. So then, if that's true, do we, you know, we did our part? No, that's not true. The Department of Energy is going to do it all. And so I got this email 3 days ago from ZX. I don't know if ZX is here. Yes, he is. And he said, "Dear Steve, I read the Nature paper with you in the room with great interest. In particular, I found the statement, integrating photovoltaics in a solar thermal absorbent may be possible, allowing both approaches to be integrated. Very appealing." Okay, so again, Arun, ARP-E, SunShot, lots of conversations, designs, plans going on. So then ZX sends me a paper 2010. There's a lot, by the way, ZX, there's a lot of other cool ideas out there. And so what he and his colleagues at Stanford have proposed is a combination of temperature, so it's thermiotic emission, you know, like vacuum tubes, you heat up the metal, electrons come out. So now you do that, and then you could have a little voltage gap, but you'll shrink it to micro integrated circuit scale technology. Light goes in, electrons pop out, they get collected, You can bias voltage. That doesn't cost any energy. And now you can let this temperature go up, which before in a standard PV would be death if the temperature goes up. But now it becomes your ally. And so it's a combination of thermionic type emission with photo. And then the light helps get you up there. So the light, the photon energy. So it's a combination of both thermionic, which is a equilibrium DC thermodynamic thing, and light to add the little boost to get you up there. Don't know if it's going to work, but hey. And then the next thing is think about what SLAC and others are now doing with photocathodes and injectors. You can make little points on this to make field effect to increase that, okay? Except in a little device. And so we hope it works, and we'll see. But there are dozens of great ideas out there. But don't count out silicon, because it still is marching down. The conventional silicon, what used to be polysilicon, they're learning how to grow this with single crystal quality, but in these big vats now, not this drawn fiber of seed Krakowski method, okay? So that's going to get to 18, it's now 16.5% quantum efficiency. It's going to go to, if you get 2/3 of a single crystalline, you're already in the 20% range, but with polysilicon prices. And then all the balance of the system scales with the overall crystal. 16 to 21%, 5%, 5 over 16, that's a real thing. But half the cost of the silicon is still the silicon. And this is a new company that's came out of stealth mode recently. And they have crystalline silicon, and they have a very, very clever layer. And then they put on chemical vapor deposition, grow up 3 to 5 microns very rapidly, and they can peel it off, but the substrate can be used over and over again. Okay? Now, 3 to 5 microns is about what you need with light trapping. So it doesn't have to be 150 to 200 microns, which is what we use today. So now you've just gone down in the cost of half the cost of the material of the module by a lot. So if this works, that would be good. All sorts of other cool ideas out there. But what if the module costs nothing? How much would it cost to put it on your roof? Well, let's take 2 examples. Residential PV in Germany costs $2.50 a watt. Residential PV in the US costs $6 a watt. Okay? The difference in the installation cost is huge, and I'll give you a hint. It's not the cost of labor. What is it? German labor is actually more expensive. Okay? What is that if your roof has a structural inspection and it goes up to a certain standard, you don't have to apply for a permit and have a person in the city or town that you live in go out and inspect your roof to make sure it doesn't fall down. It's okay. Okay, then you need an inspection after to make sure it was installed correctly. Then you need all sorts of other things. And then not only that, it's also it's a tough business. How many people have done their solar installation on a rooftop themselves? So you know that's, and they make you stand in line, and it's a DMV experience and all this other stuff. Okay, in the US. In Germany, you do it online. A one-pager, boom, okay? So here's an example of what we did figure out. If you have a licensed contractor, this is a natural gas water heater, this is a tankless water heater, and you ask which is more dangerous, this or that, I would say it's that. You can have an explosion, you can have a fire, you can have carbon monoxide. You don't need a $500 permit, and you don't need an inspection, both before and after, if you have someone that has qualified license. Okay? So there are ways, it's stuff like this that's going to be the limiting factor. So we're thinking very hard on how to lower all these costs. And so this is part of it. It's low tech, but it's necessary. And so that's one of the other things. Okay, nearing the end, approaches to biofuels, lots of ways to approaches. You take sugars and starches like sugarcane or corn, and you can turn it into ethanol. You can turn woody materials like switchgrass or miscanthus or wood chips into ethanol. You can take these woody materials and turn them to drop-in fuels for gasoline, diesel, air pool. That would be the cat's meow. This feedstock is roughly an order of magnitude more than this feedstock. This feedstock, except for sugarcane, because sugar in Brazil actually is pretty good. They fix a lot of its nitrogen. It works in Brazil, but many other places can't grow sugarcane. This is heavily energy intensive, fertilizer, plowing fields. But when you get perennial plants and things like that, you get a little bit liberated from the cost of energy. And so there are many, many ways of doing this. We have 3 bioenergy institutes that were started by the previous secretary, and I see Ray Orbach here, big supporter of that as well. This is one of them, J-Bay. There's one centered in the University of Wisconsin, one centered in Oak Ridge. And there you have biomass, you have a microbial factory, you feed it this stuff, and you hope out pops out drop-in fuels or immediate precursors to drop-in fuels like diesel and jet fuel. So there's a pilot production going in Brazil to try this out. Right now it's not economically right, so in the US, but we're working on co-products. So you create something much more valuable than fuel. Let me give you an example, much more valuable. Well, scents are super valuable, but you saturate that market. Shampoo, unless you have teenagers, you don't buy shampoo by the gallon per day. Okay, it is much more valuable, but you can use the same technologies to make shampoo stuff, and then you have a 5 or 10 year period before you saturate market, and then you can help develop and drive down the technology costs. So this is one of the things we're thinking about. There's another one-liner. I didn't find the quote in this Nature article, and it had to do with looking at the agriculture industry and seeing what they do. This is a combine. So it reaps the wheat, it threshes it, and it pours grain into this. Grain is actually medium high density quality stuff. And you can take this in this little truck, you put it in a bigger truck, and then you can actually put it in a grain elevator and store it for a couple of years. And so that the collection of wheat and also corn cobs, and that stuff, and having these storage mechanisms, these are railroad carts, actually work. And guess what? You can ship worldwide not only at $100, you can ship it at $60 a ton. So that's why grain now is a worldwide commodity. It ships very easily, and you can pour it into boats very easily. So, so the question is, can you do the same? Now, let me also show you this, show you how, this is 1975 to 2003. This is the yield of sugarcane in Brazil, and it has gone up 3 times per acre with less fertilizer input, less energy input. Just so you know, they grow sugarcane in the São Paulo region. It doesn't grow in rainforests. It's too wet. Okay, so this is how they used to ship it. I don't think you can do this in the United States. But this is what they do now. They went to a combine, just like in wheat. And so this threshes the stuff. It gets some of the higher density sugar cane, a lot of leaves and stuff they leave on the field, like they do corn stover. And they take these little trucks and they boil them in bigger trucks, and these are tractor trailer trucks, and the big trucks go to the processing plant. It's been industrialized. Okay, so there's another one-liner in that Nature paper that said, if you can get a combine that takes this woody material and compresses it to pellet size, okay, game over. You won, if it's cheap. And you can put it in those little trucks and put it in the big trucks. And then it's pellet size, just like grains and stuff, you can actually blow it in and pump it in with air and stuff, and it's storable. So if you can figure out how to pelletize it in one fell swoop where you don't have to do this and put it, there's a 30-mile radius for collecting agricultural stuff because it's light and fluffy. What is it limited by? Is it 3 miles? You can drive more than 30 miles in a day. No, it's limited by the fact that the farmer has one pickup truck. And so, and other things like that, it turns out. So, but if you go to an industrial strength where you need this combine equivalent, you can make a big deal. And all the boundary conditions then change dramatically. Okay, last little bit. I'm going to talk about artificial thing. This is Leonardo da Vinci. Looked at how birds fly. He constructed a mechanism. So the idea is you get in there like so, you jump over a cliff, you wiggle your arms and legs, and you do okay. Luckily, Leonardo da Vinci was a theorist in this respect, so he didn't do that. However, if you look at these things, and you look at the Wright brothers' first plane, and they looked at the way this bird was actually navigating, it was doing this with its wings, and the Wright brothers took that to heart, and this is called wing warping. And this was the first precursor to those flaps and ailerons, but this is how they did this. Now, there's a difference between a bird and a modern-day airplane. You notice this thing kind of looks like a bird. There's no vertical stabilizer, okay? You know why? It's because birds can't mate if you have a vertical stabilizer. So you don't have to imitate nature the full way. You can pick and choose. And today's airplanes work better than birds, except they can't do things like make little 747s. So this was an idea we've been thinking long and hard for a decade, or about, this is a photosynthetic mechanism. It's on a membrane. It actually takes sunlight and it creates chemical energy. And the question is, can you do this and create sunlight directly? And Paul Alvasados this morning gave an excellent talk about nanotechnologies and energy, and about what is happening here, and how you can use low-cost stuff to make sunlight from fuels directly. There's another approach. We can, solar energy is getting cheaper and cheaper and cheaper, and so can you use electricity in various forms, wind or solar, excess wind, for example, especially with energy storage, and you don't need the sunlight anymore, and then you fix carbon dioxide, and maybe you can get it there. So it's another program we've started. There are a number of other things in the references to the Nature article that we've got going. Second to last, third to last slide. This is the transition of energy sources in the United States. This is wood. This is coal. This is oil. This is natural gas, but natural gas is expected to increase. And so this is how it works. So what do you gather from this? Well, it takes about half a century to make a transition, roughly. Okay, and even when you have oil was really a really terrific energy source, high energy density and everything else, but it still took a while to make this transition. And so the question is, do we have a half a century? And then there's another question, because there's incumbent embedded technology and infrastructure that will slow it up, and there's an additional, the incumbents don't want to be replaced, and they will also, it's just like the horse and buggy lobbies of the past, don't want this. So the question is, are you going to wait a half a century, even when renewable energy, like wind, will be below 6 cents a kilowatt hour within the next decade, which is good. That's pretty good. It will be the second lowest cost option with natural gas at 5.5 cents. So, but you'll still have problems. The distribution system, as we know it today, can't do it. That cost, by the way, doesn't include the transmission distribution, so you have to add 15%, roughly, to that, roughly. But, okay, so here's the conclusion of that article. First, we can't rely on the cost of fossil fuels to drive it out of the market, because that technology is getting better and better. And so, and at least for the 2 or 3 or 4 decades, we think that will continue, number one. And it's an incumbent embedded technology that works very well. The Saudi oil minister, Sheikh Mohammed, said the Stone Age didn't end because we ran out of stones. It's true. Arun and I added another sentence to that. We transitioned to better solutions. And so some of these technologies I'm talking about are truly better solutions. And so we need really to help drive those better solutions, better and overall societal costs down, because they are within a stone's throw, really, so to speak, of being competitive. And we've got to accelerate that transition. We can't allow it to happen because, time's running out because of climate change risks. But I strongly feel that this means you take an economic hit. It's going to be cost effective. And then furthermore, I will stipulate that this is all high technology stuff I'm talking about. This is in our sweet spot. So, we've got a lot of brain power in the United States. So we should be paying attention to this and taking advantage of that wave G, the opportunity crisis. Okay? And finally, on the other hand, if we don't do this, if we don't change direction soon, we'll end up where we're heading. And so we are still heading where we're heading. And one last, I want to leave you with this image, one of my favorite photos taken on Christmas Eve, 1968, the first mission of Apollo to go around orbit the moon. And the last of the orbits, they turned the capsule earthward and took this picture called Earthrise, shown with up and down on the orbiting axis the way it should be shown. Now, the astronaut who took the picture said, "We came all this way to explore the moon, and the most important thing is we've discovered the Earth." Now, 2 comments. Since 1868, there's more and more compelling evidence we're changing this planet. Secondly, look around. There's not much where else to go. Neither here nor here. So we should get moving. Thank you.